Questions about anything? Well, last time I was in the middle of a exciting calculation to find that this famous integral from optics, integral of sine t over t on the whole real line. And if you look at the picture, you realize that the areas are plus and minus, and those little humps get smaller and smaller. So the alternating series test says that that integral exists as a number, and turns out that number is pi. Anyway, we're getting close to being able to deduce that. Last time I made this toy region that was going to be useful. I showed that the integral of, we have this f of z is e to the iz over z. And I showed last time that if you add up the straight line parts, L1 and L2, then you get an integral related to what we want. You get 2i times the integral from epsilon to r of sine t over t dt. That happened because sine t over t is even, and the other piece, which should be the real part, cosine t over t, is odd. And so when you add those two symmetric sides up, they cancel. And that real part goes away. Okay? And so the plan is we're going to figure out what that is somehow and let r go to infinity first, and then let epsilon go to 0 second. And we'll get the answer we want. Let's see, last time I used a Jordan's lemma argument, a more sophisticated way of estimating that integral, and showed that the integral around c sub r tends to 0 as r goes to infinity. So it kind of looks like we're going to get 0 for this answer because the Cauchy theorem on this toy region, f of z, it only has that one pole at the origin, and therefore it's analytic inside and on that toy region. And the Cauchy theorem says that integral around that whole closed loop is going to be 0. So the whole thing boils down to what's left, and that would be the integral along the little punched out circular part. I'm calling that minus c sub epsilon because it's going clockwise instead of counterclockwise. And this now we're going to show that last piece tends to something. Let's see what it tends to. This is kind of like as epsilon goes to 0, notice that that's half of a circle. If it went all the way around that circle, since it's clockwise, it would be the clockwise residue theorem. It would be minus 2 pi I times the residue of f, which turns out to be 1. I'll show that in a second. That's if it went all the way around. But it's going halfway around. And it turns out as I let epsilon go to 0, that spits out half the residue theorem if it went all the way around. So that's why that 1/2 is in front of that. So it's 1/2 minus 2 pi I times the residue. And that turns out, that residue is 1, so that turns out to be minus pi I in the limit. And when I put that all together with the Cauchy theorem, I'm going to let r go to infinity, and then I'm going to let epsilon go to 0, and I'll get exactly what I want, namely I'll get the integral from 0 to infinity is pi over 2. But that's a symmetric integral, so it's twice that to go from minus infinity to plus infinity. So we'll be done. Questions about it? Plan? Yeah.
Yeah, how do we know that the value is half because it goes halfway around?
I'm going to show that.
Oh, okay.
But that's how you remember it.
Yeah.
Okay, if it went all the way around, it'd be minus 2 pi I times residue. But in the limit, and we're going halfway around, it turns out to be half that. And that's a general fact we can use in other situations. So finally, near z equals 0, my f of z is e to the iz over z, and e to the iz is 1 plus iz minus or let's see, minus z squared over 2 factorial plus, I guess I should write it like this, iz cubed over 3 factorial plus etc. And so when I distribute the z through that, I get 1 over z plus I minus 1 over 2 factorial z minus I z squared over 3 factorial plus etc. And this thing here has the same radius of convergence as the e to the iz power series. So that this is an entire function. Let's call that h of z, and it's entire. Okay, and we read off when we do that this is the residue. I promised it would be 1. That's residue at 0 of f. Okay, and now when I integrate f on the little c epsilon, well, let's see, because h is entire, of course, it would be bounded on the unit disk. So let's say h of z is less than or equal to something on the closed unit disk. Since it's a continuous function on a compact set. And so now I can calculate, let's see, the integral along minus c sub epsilon of f of z dz. That would be minus the integral along c sub epsilon of f dz. And that would be minus the integral along c sub epsilon of 1 over z dz minus the integral along c sub epsilon of h of z dz. And of course, that's a little tiny thing, so that this thing is going to be called, we'll call this the error. Let's see, this one's going to be easy to calculate. This is going to be minus the integral from 0 to pi of 1 over epsilon e to the it, I epsilon e to the it dt. The epsilons cancel, the e to the it's cancel, and I just get I integrated from minus 0 to pi. So this is going to be equal to minus I. This, let's call...
shouldn't there be a pi on that as well?
What?
Minus I pi.
Minus I times the distance, pi. The length of the interval. Thanks. That's what I promised it was going to be. Okay. If it went all the way around, it'd be 2 pi I. So that's why it's half the usual residue theorem. Okay, let's call this curly E for error. I can estimate the curly E. So, and curly E is less than or equal to the max of H on C sub epsilon times the length, which is pi epsilon. It's half a circle. And so that's less than or equal to pi times m times epsilon when epsilon's less than 1. And that goes to 0. Okay, so we're almost done with the calculation. We have the residue theorem. Well, we have the Cauchy theorem. So we have integral L1 plus the integral L2 plus integral around c sub r plus the integral around minus c sub epsilon equals a big fat 0 by the Cauchy theorem. And so step 1 is let r go to infinity. Then this one would go to, let's see, what would these go to? This first one would go to 2I times the integral from epsilon to infinity of sine t over t dt. This one would be going to 0, and this one just stays the same. And so we would get that. And then next, we let epsilon go to 0. And then when we do that, we'd get 2I integral from 0 to infinity sine t over t dt plus 0. And now this one goes to plus minus pi I equals 0. And check. We get what we want. The integral from 0 to infinity would be pi over 2. And the whole thing would be pi. Questions about that? That's a beautiful, famous calculation. It's in every book when you talk about the residue theorem. But this is a general fact I should mention. And the proof is exactly the same as what I just did there. Let's see, it often happens that you're looking at a little punched out thing on the real line. And I'll call this the usual minus c sub epsilon. And we'll have a z naught here. And this is the real line. And we'll have a f of z has a simple pole. So a pole of order 1. That's important. Otherwise, that limit doesn't exist. Then, that same calculation shows that the integral along that clockwise thing tends to 1/2 of what it would be if it went all the way around in the residue theorem. So that would be the residue at z naught of f as epsilon goes to 0. That's a useful thing to know. Another useful thing to know is that that Jordan's lemma thing works in more generality. Let's see. That's one general fact. And here's an application of the Jordan lemma idea. Here's the theorem. For computing Fourier transforms, let's say P, I'll just do as an example here. Their PQ are going to be polynomials, and we're going to have the degree. Usually we've been doing degree of Q is 2 or more than P, but now I'm just going to make it be 1. So that's an improvement from previous things. That's instead of 2. And that's why Jordan is important here. If it were 2, this would be a snap. I've already done it, in fact. And 2, Q has no zeros on the real line. then the limit as r goes to infinity of this Fourier transform like thing, integral from minus r to r, p of x over q of x. It wouldn't be hard to put an e to the I sx here, but I'm just going to put an e to the ix. If it was sx, you could do a simple change of variables and play around with it. If s was positive, you'd do what I'm about to do. If s was negative, we'd go into a lower, an upside down d instead of an upper half plane d. Anyway, this is what you would expect. It's 2 pi I times the sum of the residues over points that are zeros of q in the upper half plane. I'll call that z plus of q, residue a, and the function would be f of z over what? Q, p of z over q of z times e to the iz. Okay, and the Jordan lemma, the only thing to show is that I can use the Jordan lemma idea. So the proof would be, I do the same old D-shaped thing. I have all these zeros. I'd make the radius big enough so that all the zeros of Q are in this D. And I'd have here a minus R to a plus R. I'll call this part C sub R and this part L. L is what I want, and when I estimate the integral along C sub R, P of Z over Q of Z, dz, I use the basic polynomial estimate. This would be less than or equal to, let's see, when I do the basic polynomial estimate, I would get like an a to the degree of p, r to the degree of p, and here I'd get, let's see, that's the right-hand side one, and then the left-hand side one for q would be give me a b, r to the degree of q. And when you do the same routine, that's the basic polynomial estimate. Right-hand side on the top and left-hand side on the bottom, times the Jordan lemma integral. Let's see. And when you do the Jordan integral, an r comes out here. And that would be the integral from 0 to pi e to the minus r sine t. And that's the thing I estimated. And that r that comes out is exactly what I need to make that thing in front bounded. And so I would get a thing that's bounded there, even though the degree of q is only one more, that r takes care of that problem. And so I can estimate that. And we control by that famous integral from 0 to pi e to the minus r sine of t dt, which goes to 0. Anyway, I won't repeat the gory details because they're very much the same as what the calculations I did in that previous thing. Questions about that? Yeah.
For the very start of your proof, is it just P of Z over Q of Z, or are we not multiplying by the E to the...
Oh yeah, remember the e to the iz is bounded in the upper half plane. Oops. Yeah, sorry about that. So recall, e to the iz is less than or equal to 1 on the upper half plane. So it's not going to mess anything up. Oh, no, wait a minute. I'm sorry. That wouldn't work. That would make it fail, because that's the basic estimate would fail because that's equal to 1 at the plus or minus r's. So that's where the sine t term comes in, exactly from the e to the iz. So sorry. Yeah, it wasn't. That was a slip.
Wait, doesn't the e to the iz come in via the
That's the function we're integrating in the residue theorem. That's f of z is the p over q times e to the iz. Let's see. There's a couple more famous examples I want to do before I move on away from this stuff. These are fun, and they're gives you good practice for using complex analysis in typical situations. But we can compute trigonometric integrals now as long as the interval is from 0 to 2 pi. Basically, any trigonometric thing I write here I'll write something kind of simple. And here's the idea. We know that cosine theta is e to the I theta plus e to the minus I theta over 2. And sine theta is e to the I theta minus e to the minus I theta over 2I. And that's equal to e to the I theta minus 1 over e to the I theta. That kind of looks like a parameterization of the unit circle. So, if I write I, that's the equal from 0 to... let's parameterize the unit circle, C, as z of theta equals e to the I theta as theta goes from 0 to 2 pi. I guess I should call that C1 since it's a unit circle. So notice that our integral here is the integral from 0 to 2 pi, so that's the right interval. And I've got sine of to the fourth. So that, and look at e to the I theta. That's my z of theta. And then I have a 1 over z of theta over 2I to the fourth power. And I'm going to put my d theta over here. I wish I had z prime of theta, which would be I e to the I theta, right here. Then that would be a complex contour integral. So I wish I had that here. And the brilliant idea is, if I wish I had that, well, why don't I just give it to myself somehow? How could I give it to myself? Well, I'm going to give it to myself here. I'll give it to myself I e to the I theta. And if I give it to myself, I have to take it away. Now I have it there. And look at, this is my... this piece right here is my that's z prime of theta d theta. That's the piece I want. And what luck, this part here is I z of theta. So I didn't change anything by multiplying by 1, but when I look at it that way, I realize, aha, this is a contour integral around the circle of radius 1, and here I have z minus 1 over z over 2I to the fourth. And here I've got 1 over I times z dz. And that's something I can calculate using the residue theorem. Let's see, that has only one pole at the origin. And it's going to be a simple, well, no, we'll see, it has a pole at the origin. So we can calculate the residue, hopefully. So this is going to be equal to 2 pi I times the residue at 0 of that function inside. Okay, let's figure out what that pole is. Let's see, if I use the binomial theorem on z minus 1 over z to the, let's see, first I'll have a 1 over 2I to the fourth. And there's another I. So I'll have this function right here is 1 over I times 2I to the fourth. And then I have to take z minus 1 over z to the fourth. Let's see, first I'll pull out the 1 over z. And then I have z minus 1 over z to the fourth. So if you use the Pascal's triangle, you get z to the fourth minus, what's the next one? 4z squared plus 6 minus 4 over z squared plus 1 over z to the fourth. Okay, and so what's that? That's, where's the I go? 1 over I. Okay, I'll just leave the 1 over I there. 1 over I. 2I to the fourth is 16. So I'll call that 1 over 16I. And then I'll distribute that 1 over z through. That'd be z cubed minus 4z plus 6 over z. There it is. That's the residue. Minus 4 over z cubed plus 1 over z to the fifth. And there it is, the residue. Well, that's the residue term. There's a 16I in front of it. So I guess this is the residue term. Residue term. And we see, therefore, that my integral is going to be 2 pi I times the residue at 0 of that function, and that's 2 pi I times 1 over 16I times 6. The i's cancel. They better, because this is a real integral, and it's 3 pi over 4. Okay. That's a fun example. And in fact, you can turn this into a method. So here's the method. Questions about that? Method. Let's suppose we have a r of zw. It's a rational function in two variables. Then then that in it. Let's see, I would have integral from 0 to 2 pi of the rational function of cosine theta, sine theta, d theta, that's equal to the integral around the unit circle of, remember, cosine theta would be z plus 1 over z over 2, and sine theta was z minus 1 over z over 2i. And that business of giving myself I e to the I theta and dividing by it gave me a 1 over I z dz. And as long as there's no bad behavior on the boundary, we can use the residue theorem. So that's a fact. And then the continuing fact is use the residue theorem if nothing bad happens on the boundary, if there are no poles. Of course, if there's poles, that integral probably doesn't even exist. So use the residue theorem if there are no poles on C1, on the circle. Questions about that? See. Okay. I haven't used log yet in an example, and so that's the next one I want to do, so you've seen it all. Of course, you haven't seen it all because there's gobs and gobs. There's a whole book of examples where they use different contours. You've seen how we can use a rectangle in one of the earlier homeworks. Rectangles sometimes come up in these calculations, cleverly chosen rectangles. Anyway, I want to calculate integral from 0 to infinity of x to the minus alpha over x plus 1 dx, where alpha is between 0 and 1. So that's a real integral. And of course, we know that x to the minus alpha stands for e to the minus alpha natural log of x when x is positive. So we're kind of thinking that we'll have an analytic function, but it's going to have to involve a complex log. So let's think. I want a z to the minus alpha. That's going to be equal to an e to the minus alpha branch of log. And the question is, what branch can I use to make this to be allowed to use residue theorem in complex analysis? And here's the answer. See, I got to choose a toy region that would be relevant. And so here's the origin, and here's the positive real axis. I'm going to choose a toy region that goes like this. I kind of think of this as a Pac-Man shape. I'll call this C sub r. This is r here. This is epsilon here. And I'm going to call this minus C sub epsilon. I'll call this top and this bottom. I like to think of that as a Pac-Man contour. Okay. that red line there is obviously screaming to be a branch cut. Then I'll have a function that's analytic inside and on that thing. And so we're going to take log 0 of z. And remember, log 0 of z is going to be, the real part's got to be the natural log of mod z, and then we plus I theta, where theta is an argument of z between 0 and 2 pi.
We need an additional condition on like how far away from the branch cut the t and pi.
No, they can get as close as they want.
Well,
We're going to let them slide in the end. So we're going to have lots of sliding going on here. R is going to go to infinity. I guess the order would be first slide t down and b up, and then let r go to infinity, and then let epsilon go to 0.
I was just wondering if we needed a variable for it.
No. So let's see. Now I have to do this. Oh, by the way, there's a pole at -1. So the residue theorem is going to be relevant. So the f of z here is e to the minus alpha, this branch of log, divided by 1 plus z. Well, I guess I prefer to write z plus 1. So that has a pole at -1. And so the residue theorem is going to tell me that. Let's call this whole thing gamma. Then the residue theorem gives me that integral around gamma of f dz equals 2 pi I times the residue at -1 of f of z. And f, that's an easy thing to calculate because it's a quotient of two analytic things, and the one at the bottom has a simple 0. So that's going to be easy to calculate. It's 2 pi I times e to the minus alpha log 0 of -1 over the derivative, which is 1. So I'm using that theorem I dwelled on last hour about if you have a quotient, you take the derivative at the bottom and the value at the top. It's that quotient. So what is this 1 coming from? This is d by dz of z plus 1 evaluated at -1. Because it's a simple 0. At z equals -1. Okay, so let's see, what is that? That is 2 pi I e to the minus alpha. The natural log of modulus of -1 is 0. And the angle there, it's between 0 and pi, would be plus I pi. That 0 right there is the natural log of the absolute value of -1. And so that's a simple number, 2 pi I times e to the minus I pi alpha. Okay, and let's see. Let's first think about the limit as the mouth closes. the top one is easy because that's where the log function would be. So let's look at the top. Top goes that way, and the bottom goes that way. And here the log would be log 0z would be the natural log of z plus I times a little tiny angle. And here the natural log would be, on the bottom, would be natural log of mod z plus I times 2 pi minus epsilon. So they look like they're going to cancel, but they don't because the log term is quite different on the bottom than it is on the top. On the top, it's going to give us exactly the integral I want. So integral along t of f of z dz is going to tend to, let's see, it'd be the integral from epsilon to r. And then that function on the top would be e to the minus alpha log. Well, that's going to be, that's going to be x to the alpha. Because the I epsilon part goes to 0, leaving me with that. And then this is x plus 1 dx. That's what we want. Okay, and let's think about the bottom. So this, as the mouth, as t slides down. To the real line. And the integral on the bottom, let's see, it's going to go it's going the other way. Let's see. It's going to the left instead of to the right. So that's going to be minus the integral along minus b. And so that's going to be minus the integral. Well, we're terrified that these are going to cancel each other. But a miracle happens and they don't because this is, let's see, I got to say this tends to, on the top we would have e to the minus alpha natural log of x plus I times 2 pi. That's the key to making this work. And the bottom we have x plus 1 dx. And that's equal to, I can pull out e to the minus alpha I 2 pi. So I 2 pi alpha. That kind of comes out in front. And the miracle is these don't cancel. And this is the integral I want. We also want this. And the miracle is they don't cancel because there's that number in front that isn't minus 1. Okay, so the last thing to do, okay, so the steps are step 1, t down, b up. Step 2, let r go to infinity. Step 3, let epsilon go to 0. Okay, and here the key is going to be the integral along c sub r of my f of z dz goes to 0 as r goes to infinity. And here, my integral along c sub epsilon minus c sub epsilon goes to 0 as epsilon goes to 0. So step 4 would be the residue, the answer. step 4, what do we get? We get that the integral along the top part would be the integral we want. X to the alpha over x plus 1 dx. And then we get minus e to the I 2 pi alpha, the integral we want. And on the right-hand side is going to be, what did I get? The residue was 2 pi I, and the residue was e to the minus I alpha pi. Okay. And so what's the integral? Let's call this I. Yeah, I already called that I. So I can factor out the I, and I get the answer. I is equal to 2 pi I e to the minus I alpha pi over 1 minus e to the I 2 pi alpha. And you can calculate that pretty easy if you multiply by, well, what I'm going to multiply by e to the I alpha pi over e to the I alpha pi. When I do that, I get I like the pi in front, so I'll put that there, and I like the 2i because it looks like sine. So I'll leave that 2i up there. And on the bottom, well, I get oh, what luck! I get e to the I alpha pi. What? Oh, what did I skip? I'm sorry. This was a minus I alpha pi. Thank heavens, because now I get what I want. I get e to the minus I alpha pi when I multiply that through. And that's 1 over the sine of something. This is equal to 1 over sine alpha pi. So this integral has kind of a nice looking answer. It's pi over sine alpha pi. So next time all I have to do is show that those integrals around the circular parts go to 0. And that'll, next time, I'll show that the integral around c sub r goes to 0, and the integral around c sub epsilon goes to 0. And the key is going to be, it's just going to be the basic polynomial estimate, but the key is that if I look at the modulus of e to the minus alpha log z, log 0 of z, let's see, that would be e to the minus alpha log mod z, that's the real part, times e to the minus alpha I something, theta. And that's e to the minus alpha log z in modulus, which is z to the alpha. Mod z to the alpha. Mod z to the... Am I screwing this up? It's the